Welcome back. So we'll continue our discussion on power in the AC systems. Last time we looked at power and basically came up with two terms, the instantaneous power and the average power. And the instantaneous power and the average power were basically given by these relationships. We saw that the instantaneous power had both a AC component that went at twice the frequency of the voltage and the current, and a DC component. The DC component of the instantaneous power was called average power. And in the last video, we also took the average power and defined the term RMS and rewrote average power as VRMS, IRMS, cosine theta V minus theta I. Now, today we'll continue our discussion on other types of power. And one of the things that we mentioned in the last video was when we were looking at instantaneous power of a mixed reactive, mixed inductive resistive, or a mixed capacitive resistive circuit, we saw that there was instantaneous power on the positive side of the x-axis of the y-axis, but there was some on the negative side. So we said that average power didn't quite capture everything related to power in an AC system. So we've defined instantaneous power, average power. So let's continue with our discussion of uh, AC circuits. So AC loads can have impedance, which is basically resistance, and reactance. Reactance is basically the inductance or the capacitance, and so forth. So we've discussed these before. And now the resistance is responsible for the consumption of the average power, whereas there's this factor in the impedance called reactance, which is responsible for another type of power, and that another type of power is called a reactive power. And the reactive power, the symbol is given as Q. It basically is the power that's exchanged between reactive components like an inductor or a capacitor and the power supply. So energy comes in, energy gets transferred back from an inductor back to the power supply, and so forth. So whatever power is exchanged between a reactive component and the power supply, it's called reactive power. The symbol, like I mentioned, is Q, and the reactive power is given by 1 half V naught I naught, where V naught and I naught are the peaks, sine of theta V minus theta I. So instead of our average power was 1 half V naught I naught cosine of theta V minus theta I, where the theta V and theta I are the phase angles of the voltage and the current, uh, whereas the reactive power is the sine of theta V minus theta I. We can also write these in RMS forms. Uh, so, well, voltage and current multiplied together, we've been using the term power and assigning it a unit of watts. Now, in order to distinguish between what we call real power or average power, which has the unit of watts, and this new power definition of reactive power, we, instead of using watts, will use a unit called VAR, VAR, which stands for volt amps reactive. And it's basically a way to distinguish when we see some kind of power numbers. It is a way to distinguish between average power or real power versus reactive power. But that's the only purpose. So the unit is given for reactive power is given as VAR. Now, in a purely resistive load, okay, in a purely resistive load, which means in the case of an impedance, we have impedance is resistance plus J reactance. A purely resistive load, the J reactance is equal to 0, so the only thing that exists is the resistance. So in other words, the power that's burned is only average power. There's no Q in this case, because there is no imaginary term in the impedance of a resistor. Now, in the case of a purely capacitive, there is no resistance. So the real term of the impedance is equal to 0. So pure capacitive loads uh, have no average power consumption, but Q is less than 0. And for inductive, the reactive power Q is greater than 0, and that basically comes from the voltage leading versus lagging. So this sign, basically this thing right here, controls the sign of the reactive power. So if the reactive power is negative, that's a capacitive load. If the reactive power is positive, that's an inductive load, and we can figure that out by basically looking at this sign of the voltage. Okay, so that's reactive power. So we've defined so far three power terms: instantaneous power, average power P with a unit of watts, a reactive power Q with a unit of volt amp reactive. Now, since average power tells us the real part, so power dissipated by the real component of the impedance, and the reactive power tells us the power exchanged by the reactive component of the impedance or the imaginary part of the impedance. Uh, well, there's something called complex power, which basically takes these two powers, the P and the Q, and rewrites it as the following. So the complex power, which has a symbol of S, is basically the pure P plus JQ. Well, P plus JQ. Now P is so I'm going to write only in terms of RMS, VRMS, IRMS, and the cosine, whereas Q is VRMS, IRMS, and the sine of the difference between the voltage and the current phases. Now, so this is the real part, and that's the imaginary part of S. Uh, this part is the real power. That part is the reactive power. This part P has a unit of watt. This part Q has a unit of volt amp reactive. So complex power S, in order to distinguish this again, has units of simply called volt amps or VA. Okay, so this is something to keep in mind, is that the complex power, reactive power, real power are all multiples of voltage and current, but because of the sines and the cosines and the imaginary terms, in order to distinguish them, we use different units. Real power, watts; reactive power, volt amp reactive, var; and complex power is VA, volt amps. Okay, so that's something to keep in mind. Now, the complex power can also be written in terms of phasors. So if we think of the voltage phasor V and the current phasor I, by definition, complex power S absorbed by the AC load is 1/2 the product of the voltage phasor and the complex conjugate of the current phasor. So need to keep in mind that the current that's used in complex power expression, if you're going on the phasor direction, is the complex conjugate. So the I with the star basically means the complex conjugate, right? So complex conjugate basically means if you have a complex number such as P plus JQ, the complex conjugate of that number is P minus JQ. So the magnitude stays the same, but the angles change sign, right? So basically expanding this from RMS, S equals VRMS times the complex conjugate of the current IRMS, VRMS, so that's phasor, by the way, since it's in bold. So VRMS phasor basically has a magnitude called VRMS and an angle called delta V, uh, uh, theta V. IRMS conjugate has a magnitude of IRMS, but the angle is negative theta I. So when two phasors multiply, the uh, the the magnitude simply multiply. So we have VRMS, IRMS. The angles add up. So we have theta V minus theta I as the angle of S. Now, going from this is in polar coordinates. If you want to write that in terms of Cartesian coordinates, you can take the magnitude cosine of this angle plus j magnitude sine of this angle. And this is where we started off earlier in terms of S equals P plus JQ. Right? So we have S plus equals P plus JQ. So we've said that this is a complex power now. P plus JQ. Now P is in the real axis, Q is in the imaginary axis. So let's draw that. So let's draw this right here. So here's P. Uh, so according to this, here's P, here's Q, and the angle, this angle right here is theta V minus theta I, right? This triangle that's formed between P and Q and the S, so that's the magnitude of S, and that magnitude of S is actually called apparent power. So the magnitude of S is called apparent power, and this triangle is called a power triangle. So the magnitude, this vector right here, of the complex power is a vector, so the magnitude of that complex vector S, magnitude S is called apparent power. It simply is VRMS IRMS. If you take the if you actually take the magnitude of this, this triangle is called a power triangle. This angle right here, theta v minus theta I, if you take the cosine of that angle, that basically means a new term called a power factor. So power factor is basically defined as the cosine of theta v minus theta I. Okay. Uh, Sine of theta v minus theta I has another name. It's called reactive factor, but we will ignore that for now. So we'll just talk about the power factor in a second. So this particular representation of real power and imaginary power, or real power and reactive power in this triangular form is called the power triangle. Okay, so power factor is of a load is basically, as I mentioned, defined as the cosine of the phase difference between the voltage across the load and current through the load. So that's PF is the short form for power factor. Now, for a purely resistive load, since the voltage and currents are in sync, uh, theta v minus theta I is equal to 0, so cosine of 0 leads us to a 1, so we get a power factor of 1 for a purely resistive load. Whereas for a circuit that has a reactive load, for a purely reactive load, such as a capacitor or an inductor, the voltage leads or lags by 90 degrees, so we'll end up with either cosine of positive 90 or cosine of negative 90 in here, which leads us to a power factor of 0. Okay, so if we have a mixed circuit where we have resistive elements as well as reactive elements, then our power factor will be somewhere in between 0, which is purely capacitive inductive or purely reactive, and 1, which is purely resistive. Okay, now delta V minus theta I, since the negative angle, since the cosine of the negative angle, that's when the current leads the voltage in a capacitive load, is still a positive result. So we still get a positive result. We use the term PF leading to represent this case. So for a capacitive load, we call it power factor leading, and for an inductive load, we call it power factor lagging. Ideally, we prefer the power factor to be a 1. A load with a lower power factor basically means that it requires more current from the source to produce the same amount of average power or useful power than the load that has a power factor of 1. Okay, so ideally we want a power factor of 1. Now consider a 240 watt motor that you're trying to connect to a 120 volt RMS source, right? If let's look at what the difference is if a power factor of 1 versus a power factor of 0.8, right? So if we have power, which is we're given 240 watts, so that's real power. VRMS is given as 120 volts, so IRMS times the power factor 1 leads us to IRMS calculation of 2 amps. So if my power factor is 1, then the current demand from the source is just simply 2 amps. If my power factor is 0.8 lagging or leading, let's say, so the current that my load demands from the source just went up from 2 amps to 2.5 amps. Right? So here is a plot of IRMS versus the power factor. So this is power factor of 1, which leads me to a load demand, current demanded from the source to be simply 2 amps. If I start to lower the power factor, I see that I am demanding more and more current from the source. Okay, and that's not necessarily a good thing. Okay, so we'll do a couple of examples in next video related to these different power terms. A couple of a quick summary to keep in mind. AC power systems have a different uh, uh, a name for different situations of power. We have instantaneous power that tells us the power at any given time. The average power of a AC system is basically the power dissipated in the resistive portion of the impedance. We have a reactive power called Q, whose unit is volt amp reactive. That tells us the power that's exchanged with the reactive elements that are in the circuit. We have the real component and the reactive component of the power, which combines to form what is known as complex power S. We can draw that relationship in a triangle form called the power triangle. And from the power triangle, we can refer to a term called the power factor, which is basically the cosine cosine of theta v minus theta I, and the power factor is important concept.